Hello everyone. So we discussed the heat pumps, the heat engines, which converts the heat into the work through a cyclic process. And we haven't really discussed much about the second law of thermodynamics applied to that. So the second law of thermodynamics, which applies to heat engines, is called Kelvin-Planck Statement. And what it says is that it's impossible for any device that operate on a cycle receive heat from a single reservoir and produce a net amount of work. And with that, it means that you should have some heat rejection to a low temperature source, to a low temperature sink, in order for your cycle to be completed. So the idea is that this basically devices operate on a cycle. So it means that the initial temperature and the final temperatures are the same. So in order for your temperature to come back to the same pressure that you had initially, you have to reject some heat to a low temperature sink. And what this Kelvin-Planck statement tells is basically the same thing. If you have a high temperature source at high temperature, and then it goes and then produce some, go to the heat engine and produce some amount of work, W net out, then what this statement tells you is that whatever heat is being lost here is not equal to 0. So this heat loss, and here is QH, which you get heat from the source. So this QL is not 0. That's basically what the second law of thermodynamics says. So there should be a heat rejection to a low temperature sink, okay, for the heat engines. So you can see in this picture, this heat engine violates the second law of thermodynamics because it doesn't lose any heat to a low temperature sink. Okay, so that's the second law of thermodynamics, Kelvin-Planck statement. Next, we want to talk about the other statement of second law of thermodynamics, which is basically Clausius statement. But first, let's introduce some of the devices that operate based on that. Refrigerators and heat pumps are those devices. So what does refrigerator does? Refrigerator transfer heat from a low temperature medium to a high temperature one, right? So remember we talked about this. If you the heat can be transferred from a high temperature source to a low temperature area automatically, right? You don't need to do any work or anything. This process is automatic. But if you want to transfer heat from a low temperature medium to a high temperature one, then you need some special device. One of those devices is refrigerator, right? So how does it work? It operates in a cycle again, and one of the most famous refrigeration cycle is called vapor compression refrigeration cycle. And it has a condenser, it has a compressor, it has a condenser, it has an expansion valve, and it has an evaporator. So the working fluid in these devices are refrigerant. Remember R134A that we were discussing in previous chapters, and that's one of those refrigerant. So the refrigerant enters the compressor initially, and the compressor increases the pressure of the refrigerant. So based on simple equation of state PV and RT, if your pressure increases while your volume stays the same, then the temperature should go up, right? So you can see after the compression process, the temperature of your system increases, the pressure of your system, pressure of your working fluid, I should say, and temperature of working fluid increases, and then it enters an area which is condenser, right? Condenser basically drops the temperature and loses the heat to the environment. It could be kitchen air or surrounding air, and then you can see the pressure stays constant, the temperature drops, and then it enters an expansion valve. So the expansion valve drops the temperature significantly, drops the pressure significantly, and then it enters an evaporator. So evaporator absorb the heat from the refrigerated space, and because of very low temperature and pressure it has, the working fluid has, in the evaporator it absorbs the heat from the space, which is in our case is the refrigerated space. So and then again it goes back to the compressor. So that's a full cycle of a refrigeration process. So again, you see a compressor, condenser, expansion valve, and evaporator. Condenser, usually you probably have seen it, the coil tubing that you see on the back of the refrigeration. If you put your hand there, you see it's hot, right? That's basically where the condenser is. And refrigerated space, of course, is within your inside your refrigeration. And you probably if you are familiar with refrigerators, you know that they have a compressor as well, right? So this is the refrigeration, and the purpose of refrigeration is to absorb the heat from refrigerated space, right? So our desired output is to increase QL, right? So we can define an efficiency. The efficiency of the refrigerator is usually reported in terms of another factor, which is called coefficient of performance. The reason for that is that the coefficient of performance could be higher than 1, but efficiency based on the common practice is less than 1. So the reason that they move from efficiency to a coefficient of performance is that coefficient of performance is more than 1 and could be more than 1, and usually it's more than 1, and efficiency is less than 1. So okay, so but the definition is the same. The definition of coefficient of performance is desired output divided by required input. So again, in a refrigeration process, we have QL as our desired output, and required input is W net in. Same as heat engines, W net is QH minus QL. It's a cycle again. If you have your whole system as your basically system, so if you have all of these devices, expansion valve, condenser, compressor, and evaporator, as one single system, then there is it's a closed system. You have heat absorbed from the refrigerated space, heat goes into the environment, W net in to the compressor, right? So W net is equal to QH minus QL, and what you have here is QL over W net, which is this definition, and it results into this equation for coefficient of performance of refrigerators. Now, we mentioned that the COPR could be greater than 1. The reason is that the denominator of this equation could be less than 1, right? And then 1 over a number less than 1 is, of course, higher than 1. So for the refrigeration process, as opposed to what we had in heat engines, QH could be smaller than QL. So the amount of heat that you absorb from the cold refrigerator space could be higher than what you basically the amount of heat that you get from the the cold refrigerator could be higher than the amount of work that you basically input to your system. So QL could be higher than W net in. Therefore, COPR is could be greater than 1. All right, so the next one is heat pumps. So heat pumps are devices that the principle is basically same as refrigeration, except that in the refrigeration process, you want to keep some area cold by absorbing heat from a high temperature area. The heat pumps work kind of reverse. You want to heat up some space by absorbing heat from a low temperature area. So for example, air conditioners, right? Air conditioners try to absorb heat from a cold area outside of your house and try to increase the temperature or keep the high temperature of your house constant, right? So these are called heat pumps. So the desired output of the heat pumps are whatever heat they are inputting into your house, which is QH, right? And the required input, of course, is W net, right? So we can define the COP, coefficient of performance of heat pumps, using this equation. And if your device, let's say you have a heat pump and then you have a refrigerator, and they have the same QL, they have the same QH. You can use combine this equation with this equation and find that the coefficient of performance of heat pumps is always greater than 1, and it's related to the coefficients of performance of refrigerators by this equation. Okay. Alright, so that is the heat pumps, and in the next video we will continue on the discussion of heat pumps and refrigerators, and we will define the Clausius statement of second law of thermodynamics.